Good morning, dear students, and welcome back to our course. In the last lecture, we discussed the preparation strategy which we need to follow in order to prepare for the GATE exam, and we also discussed the syllabus of electrical engineering student as well as for electronics and communication engineering students. And I told you that as far as GATE paper is concerned, we have basically three main section. First one is aptitude, followed by English, and the total marks allotted for this particular section is 15 marks. Then we have applied mathematics section, which is of 15 marks, and then we have technical domain of total 70 marks. So if you add, you will get 100 marks, and to clear this particular exam minimum you need to score 30 to 35 marks irrespective of your category. I'm talking in general. So to clear this particular exam, let us have a target to score at least 30 to 35 marks on paper in order to clear this particular exam. And in the last lecture I also informed you that while preparing for this particular exam, you have to focus on aptitude, English as well as applied mathematics. So these two sections are very, very important, because if you add these two sections, the total is 30. And to clear this exam, you have to score at least 30 marks. So if you have not prepared for technical domain, then only, or it may possible that you will clear this particular exam even if you have not prepared for the technical aspect. The thing is that you have to prepare for aptitude, English as well as applied mathematics. So this is very, very important. Now let us try to discuss the actual syllabus of GATE. And I told you that in the last lecture I have prepared some 40 lectures teaching plan, where I'm going to cover some fundamental aspect related to network theory and related to control system engineering. And I told you that these two courses are very much important as far as electrical as well as electronics and communication engineering students are concerned. So, first 14 to 15 lectures are from network theory, and the remaining 25 to 26 lectures are from control system engineering. So, let us begin with our today's session. So, the course which I am going to take in the first 12 to 14 lectures are from network theory, or sometimes this particular course is also called as circuit theory. So, circuit theory. So, first of all, let us try to discuss what is the difference between network and circuit, whether these two terms are exactly the same or if they have a difference. So what exactly the difference between network and circuit, that we will first discuss, and then in the same session we are going to discuss the fundamental operating parameters which plays an important role in order to analyze the behavior of any circuit. So what exactly network is? So to understand this particular topic, let us consider a structure. For example, if you have a structure where we have a source, then we have a switch, and to this switch we have connected a resistor of value R1, and to this again I have connected one more resistor in this fashion. Let us consider that the value of this resistor is say R2, and then we have one more resistors indicated by symbol R3, and then here we have one more source indicated by symbol say S2 because this is source 2 and this is source 1, and the path is completed like this. So this is what we have a structure, and our objective is to identify whether this particular structure is network or whether this structure is a circuit. So first of all, we need to identify that how many number of elements are there in this particular structure. So from this diagram, it is very clear that here we have total 3 plus 2, 5 element, out of which 3 elements are passive and 2 elements are active. Now, why they are called as active and why they are called as passive, that we are going to discuss in the coming session. But for time being, let us consider that the resistor R1, R3 and R2 are nothing but passive element because they are going to consume energy, they are not going to supply energy, whereas element S1 and element S2 are considered to be a active element because they are going to supply the energy. Now, if you see this structure very carefully, in this structure we have a combination of open loop as well as closed loop pattern. See here, initially when this switch is open, the value of current flowing through resistor R1, let us consider that the value is say I1 is going to be 0. Why it is going to be 0? Because initially the switch is open, hence path is not completed, or I can treat this particular portion of structure as open loop. While if you consider this particular section of the structure, because in this particular case we have one more source which is connected over here and the source is indicated by symbol S2, because of this it is trying to maintain a flow of current in this particular circuit like this. Let us consider that this current is say I2, and the value of I2 is decided by the effective resistance of R3 followed by R2. So because in this particular portion we have 3 elements, first one is your source S2 followed by 2 passive element R2 and R3, and through each element there will be a finite value of current flowing through the circuit which is nothing but I2. That's why this particular portion we can treat as a closed loop structure or closed loop portion of a given structure. Now, what is network? Network is nothing but a kind of structure which has a combination of open loop followed by closed loop. Then this type of structures are called as network. Now, suppose if I close this particular switch, for example, if I close this switch, the moment I close this switch, what will happen? This source S1 now physically as well as electrically get connected to the circuit. Now we can say that the value of I1 is not exactly going to be 0. It has some finite value. That means in this particular structure, now each and every element is going to carry some finite value of current. That means in this particular structure, we don't have the concept of open loop. We have only closed loop. Now this particular structure we can treat as a circuit. So what is the basic difference between network and circuit? Network is going to be a combination of open loop followed by closed loop, whereas circuit is always going to be a closed loop. So I can say that all circuits are network, because if you have a structure and in that particular structure all elements are going to carry a finite value of current, I can treat that particular structure as a circuit or a network. But all network need not to be a circuit, because in network we have a combination of open loop followed by closed loop. So if you have only closed loop, then that particular network we can treat as a circuit. So in case of circuit, if you have say 5 elements, All five elements are going to carry some finite value of current. If we have 10 element, then all those 10 elements are going to carry some finite value of current. So that is nothing but circuit. So this is very important, and you should have a basic understanding between what exactly the network is and what exactly the circuit is. Once we have understand this concept, that is the difference between network and the circuit, now let us try to understand the fundamental operating parameters which plays an important role in order to analyze a given circuit, or you can say a network. So network, which is a combination of open loop followed by closed loop, whereas circuit where we have only closed loop. Now the first definition which I'm going to explain you all is nothing but electric charge. What exactly the meaning of this electric charge? Normally it is indicated by symbol Q. So what is electric charge, or what is nothing but charge? So charge are nothing but a property of atomic particle, or sometimes it is nothing but a kind of property because of which a body is going to experience a force in the presence of electric field. For example, if you have an atom, and if this particular atom is going to placed in the presence of applied electric field, by the virtue of its property, which is nothing but electric charge, this particular atom is experiencing a force. So that property is known as electric charge. And normally it is indicated by symbol Q. Now let us try to understand how to assign a net positive charge or a net negative charge to an atom. And for that, we need to deal with the basic configuration of an atom. We know that an atom is consists of three fundamental components in it. First one is called as proton, which carry positive charge. Then we have electron, which carry negative charge. Then we have neutron, which carry no charge, or you can say zero charge. And we know that within an atom, the number of proton and the number of electrons are always going to be equal. That means the count of positive charge and the count of negative charge within an atom are always going to be same. Hence, they will cancel out each other, and the net charge available on an atom is always going to be a zero. And that is the reason if you touch any metallic body, you do not feel any kind of shock. The reason is that the count of net positive charge and the net negative charge within that particular element is always going to be the same, and hence they will cancel out each other, and there will be no net charge on an atom. But due to some method, suppose we create the deficiency of electron, or we add excess amount of electron within an atom, then in that particular case, it may possible that the atom is going to achieve a net positive charge or a net negative charge. For example, if you have an atom, and due to some technique, if we create the deficiency of an electron, deficiency of an electron means what? The number of protons are now more than number of electrons. So this particular atom is going to achieve a net positive charge. In the same way, if we have an atom, and if we create excess number of electron within that particular structure or atom, then in that case what will happen? The number of electrons are going to be more as compared to proton. So this particular charge or this particular atom is going to achieve a net negative charge. So by doing this particular technique, we are in a position to have the flexibility to provide a net positive charge or a net negative charge on an atom. So this is very important. So what is charge? Charge is basically a fundamental property of an atomic particle by the virtue of which it is going to experience a force when it is placed in the presence of electric field. This is very important. Now let us try to discuss another definition. But before that, what will be the unit for electric charge? The unit for electric charge is nothing but coulomb. And we know that the charge occupied by one proton, or you can say 1p, is always going to be equal to 1.6 into 10 to the power minus 19, and the unit for charge is coulomb. In the same way, if you are interested to find out what will be the net charge on one electron, so it is going to be equal to 1.6 into 10 to the power minus 19 coulomb. So magnitude wise they are nothing but same, but there is a difference between positive and negative. Because it is proton, it has a net positive charge, and because it is neutron, it has a net negative charge. This you have to remember. So magnitude wise they are exactly the same, which is 1.6 10 to the power minus 19 coulomb, but for proton it is positive and for electron it is negative. So electric charge is a fundamental property of an atomic particle by the virtue of which it is going to experience a force when it is placed in the presence of electric field, and then the unit of electric charge is nothing but coulomb. This is very important. Now let us try to discuss the another definition, which is the definition of current, or what is electric current. So how to define electric current? So what is current? So current are normally indicated by symbol I, and the unit for current is ampere, A. So how to define electric current? So electric current is defined as I is nothing but rate of change of charge, or it is simply Q by T. So what is electric current? Electric current is nothing but a rate of flow of charge within a given closed path, or simply it is Q by T. And what would be the another unit for electric current? Because charge is coulomb, suppose time we specify in second, so coulomb per second will be the unit for current. But normally we define the unit of current is ampere. So this is very important. Now let us try to discuss what is the sign convention which we need to follow in order to identify the direction of current flowing through a given circuit. For example, if you have a closed path section like this, and suppose this particular point is say A and this particular point is say B, and in this particular portion the value of current is flowing from point A to point B, and the value and the magnitude of that particular current is say 2 ampere. So this is what the actual scenario. We have a portion of a network indicated by symbol AB, and through this particular section there will be a flow of current which is of 2 ampere, and the direction is from A to B. Now suppose I want to indicate the same structure but in reverse direction. How I can represent that? Here this point is say B, and here this point is say A. So I know that initially the value of current flowing through the structure is from point A to B, and the magnitude of that particular current is 2 ampere. So suppose I indicate that particular current flow in opposite direction, that is from B to A, then in that particular case I need to take this as minus of 2 ampere. So this minus term indicate that the projected direction mentioned in this particular section is not actual direction of the current. The actual direction of current is from A to B, which is of 2 ampere. But because I have indicated the direction is from B to A, that's why I need to add negative sign. So कहने का मतलब ऐसा है कि आपके पास में अगर मान लो एक सेक्शन है, और वो सेक्शन के अंदर में आपका एक्चुअल करंट अपवर्ड डायरेक्शन में फ्लो हो रहा है having a magnitude of 2 ampere. Suppose in the same section if you want to indicate the value of current flowing in the downward direction, then it has to be minus 2 ampere. This is very very important. So this sign convention we need to follow in order to analyze a given network or a given circuit. It is very important. Now let us try to discuss another definition of electrical network, which is nothing but the concept of potential. What exactly electric potential is? So I'm writing here electric potential, or sometimes this particular term is also called as voltage, indicated by symbol V, and the unit is volt. So what is the meaning of this? What is the meaning of electric potential? So electric potential is defined as energy per unit charge. This is the simple definition of electric potential. Now, energy, suppose we define in terms of E, and charge we define in terms of, say, Q. So, energy per unit charge is nothing but electric potential. Now, let us try to identify the unit for electric potential. I told you that the unit for electric potential is nothing but volt. So what will be the alternate unit for this? Now see here, ultimately from the definition it is very clear that electric potential is nothing but the ratio of energy per unit charge. Now suppose if we define energy in terms of joule, and we know that the unit of charge is nothing but, say, coulomb. So joule per coulomb is nothing but the alternate unit for electric potential, or I can write here as 1 volt is exactly going to be equal to 1 joule per coulomb. This is very important. Now, what is the significance of this? Now, I told you that in order to flow a current through a circuit, for example, if you have a circuit and we are considering a portion of that particular circuit indicated by symbol AB, and suppose if you want to flow a current from point A to point B. So this is possible when we create a momentum of charge with respect to time. That means we create a flow of charge from point A to point B. Now we know that in order to create a flow of charge, we require some energy, because without energy, it is not possible to flow a charge from point A to point B. Then, how much amount of energy we have maintained per unit charge in order to create a flow of charge from point A to point B defines electric potential, which is nothing but V. So when I say that we have electric potential of, say, 2 volt, so I can write here as this 2 volt, I can replace this by joule per coulomb. So I can say that we are maintaining 2 joule of energy on each charge in order to complete its path from point A to point B, or within that particular circuit. So this is what the beauty of electric potential. So the unit of electric potential is nothing but volt, or we may specify this particular term as joule per coulomb. This is very, very important. Now let us try to understand the sign convention for electric potential. How to do that? Just like in case of current, in the same way we have the sign conventions for voltage. So how to implement that? So to understand the concept of voltage drop and voltage rise, voltage drop and voltage rise, voltage rise. What is the meaning of this? See here, voltage drop and voltage rise are nothing but a sense of reading a circuit. For example, here I have considered a simple passive element indicated by symbol capital R, which is nothing but a resistor. And suppose to this particular resistor, I have passed a finite value of current indicated by symbol I. And according to Ohm's law, there will be a voltage which will be developed across this particular resistor, and the value is V equals to what? I into R. Now we know that current is always flows from higher potential to lower potential. So, but obviously this point is going to be plus and this point is going to be minus. Now this is nothing but V, where V is I into R. Now, let us try to understand what exactly the meaning of voltage drop and what exactly the meaning of voltage rise. Now, suppose this positive terminal, I have treated this as a higher side indicated by symbol 1, and this negative terminal I have indicated as a lower side. Let us consider that this particular term is nothing but, say, 0. So when we are at plus, we are at 1, higher side. When we are at minus, we are at 0, which is nothing but lower side. Now suppose I want to read this particular element. I want to read this circuit. So there are two possibilities to read this circuit. I may start reading from point A to point B like this, or it may possible that I may read this particular element from B to A like this. Now, depending upon what sense I have implemented in order to read this particular circuit, I may experience a voltage rise or I may experience a voltage drop, but of same magnitude, which is nothing but V equals to what? I into R. Now, for example, if I read this particular element from point A to point B, where point A is over here and point B is over here. So, when I move from point A to point B, basically I am moving from higher point to lower point. That means in the direction of current. So, initially when I say we are at higher, that means we are at level 1. And when we are at point B, we are basically at negative terminal. That means we are at level 0. So we are moving from 1 to 0. So we will experience a drop in voltage. So this is known as voltage drop. That means when we are moving in the direction of current, so current always flows from higher potential to lower potential. So we will experience a voltage drop, and the magnitude of that voltage drop is always going to be equal to I into R, where I is the value of current flowing through that particular element and R indicate the effective resistance of that particular element. In the same way, it may possible that we may read this particular circuit or element in the opposite direction. That means when we read this circuit from point B to point A, so point B is at lower, which is nothing but negative. Point A is at higher, which is nothing but positive. So when we are moving in the opposite direction of current, because actually the flow of current is from higher to lower, but we are moving or we are reading this particular element in the opposite direction of current, that is from level 0 to level 1. So in this case, we will experience a rise in voltage. So this is known as voltage rise, and the magnitude is again going to be same, which is nothing but I into R. So I can say that in the same situation, when we are moving in the direction of current, so moving in the direction of current, we will always experience a voltage drop. And when we are moving in the opposite direction of current, because current is always flows from higher potential to lower, and when I say that we are moving in the opposite direction of current, that means we are moving from lower to higher, so we will experience a voltage rise. And magnitude wise, both are nothing but same, which is nothing but I into R, where I is the value of current flowing to that particular element and R indicate the effective resistance of that particular element. The thing is that we just want to provide a sense of reading that particular circuit. If we take voltage drop as positive, then voltage rise has to be negative. Or if you take voltage rise as positive, then in that case we need to take voltage drop as negative. So these are the sign conventions which we need to implement in order to analyze given circuit. So normally I prefer this sign convention in order to follow a network analysis procedure. That means whenever in the circuit we will experience a voltage drop, we are going to take that particular term as negative. And whenever in the circuit we will experience a voltage rise, we are going to take that particular term as positive. So this you have to remember. This is very important. Now let us try to discuss the another topic or terminology, which is nothing but the concept of potential difference. Now, how to define potential difference? So, to understand this, let us consider that we have two terminal. Let us consider that this terminal is maintained at A, and somewhere over here we have terminal B. And here, our objective is to understand the concept of potential difference. So, what is the meaning of this? See, As far as general terminologies are concerned, potential difference is simply the difference between the potential available at two different points, not more than that. So, what is potential difference? It is simply the difference between potential at two different points. So, here we have 2 points at A and at B. Let us consider that the potential available at point A, which is nothing but VA, is indicated by symbol VA, and the magnitude of that particular value or electric potential is say 15 volt. And suppose the potential at point B is indicated by symbol VB, and let us consider that the magnitude is say 20 volt. And suppose if you want to find out what will be the potential difference between point B and point A, so how we can write that? So I can write this as VBA, which is going to be equal to VB minus VA. Or what is the value of VB? It is going to be 20 volt minus what is the value of VA? It is 15 volt. So 15, 20 minus 15, this is nothing but 5 volts. So the potential difference between terminal A and B is nothing but plus 5 volt. So plus 5 volt means what? B is at higher potential, A is at lower potential. So when we connect a element in between these two terminal, this particular element will experience a voltage of around 5 volt. And because this terminal is at higher point, this particular terminal is at lower point, so current will always flows from higher potential to lower potential. So the value of current flowing through this particular circuit is nothing but I. And let us consider that the resistance of this particular element is say R. So I can write here as V equals to what? I into R. And in this case, this V is going to be equal to 5 volt, because the potential difference between these 2 points we have maintained as 5 volt. This is very important. Now, what is the physical significance of this? So I can write this 5 volt as 5 joule per coulomb, because from the previous definition we know that electric potential is nothing but energy per unit charge. Energy is joule, charge is nothing but coulomb. So 5 volt is always equivalent to 5 joule per coulomb. That means in this particular case, we have maintained 5 joule of energy on each charge in order to complete its path. That means if a charge wants to flow from point B to point A, we are maintaining 5 joule of energy on each particular charge. So this is what the beauty of potential difference. And the unit of potential difference is again going to be what? Volt. This is very, very important. Now, the next definition which we need to discuss is the concept of power. How to define power? What is the meaning of power? To understand this, I am writing electric power indicated by symbol P. Now, from the definition of fundamental physics, we know that power is basically energy per unit time. So I can write here as E by T. Now, let this will be your equation number 1. And we know that the relationship between voltage, energy and charge. We can write voltage as energy per unit charge. So from this equation, I can modify this as energy is equals to voltage times charge. Let this will be your equation number 2. Now if you combine equation 1 and 2, what we will write? We can write here as power is equals to energy per unit time, but energy is voltage into charge per unit time. Or I can rearrange this particular term as voltage into charge per unit time. Now we know that this charge per unit time is nothing but what? It is current simply, because current is nothing but rate of flow of charge or charge per unit time. So I can write this power as V into I. That is the reason in electrical domain we always write power is simply a product of voltage and current. But remember one thing, this particular definition is for DC circuit only. In case of AC, we need to define the nature of power. That means we are dealing with active, reactive, or apparent. Then in that case, we have to take care of power factor. But for time being, let us consider that in case of electrical circuit, as far as DC nature is concerned, the definition of power is simply a product of voltage followed by current. Now, what will be the unit of power? Now, see here, power is simply a product of V and I. The unit of V is volt and the unit of I is ampere. So, volt ampere will be the unit for power. But in some cases, power is also defined in terms of watt or simply W, capital W. So, watt as well as volt ampere are nothing but the unit for power. But remember one thing, again I am informing you that this is for DC circuit. In case of AC, we have active, apparent, and reactive power. That we are going to discuss in the coming sessions when we are dealing with AC circuits. But for time being, the definition of power for DC is V into I, which is very, very important. Now let us try to analyze some more mathematical formula to calculate the value of power. For example, if you have a resistor indicated by symbol capital R, where capital R indicate the resistance of that particular resistor, and suppose this particular point is maintained at higher polarity and this point is maintained at lower polarity, so there will be a flow of current because path is complete, and there will be a potential difference, so there will be a flow of current from higher potential to lower potential. The moment there will be a flow of current, this particular resistor will experience a voltage, and according to Ohm's law we can write this V is equals to what? I into R, where I is the value of current flowing through this particular resistor and R is the effective resistance of this particular element. Now, I can rewrite this particular equation. This equation, let us consider this equation is say 1. So, power is volt into current. So, according to Ohm's law, we can write this V as I into R. So, I can replace this voltage as I into R. So, another definition for power is going to be I square into R. This is very, very important. Let this will be your equation number 2. In the same way, I can replace this current as V by R. So if you replace this current as V by R in equation number 1, another definition to calculate power is nothing but V square divided by R. So this is another formula. That this will be your equation number 3 in order to calculate the value of what? Power. So basically we have 3 formulas to calculate the value of power. First one is Vi, second one is I square into R, and third one is V square by R. So I'm writing this. P is nothing but V into I, or we can write this as I square into R, or I can write this as V square divided by R. So you should know at what point we have to apply which of the following formula. The process is very simple. In order to calculate the value of power across any particular element, the thing is that we have to take care of voltage across that particular element, as well as what will be the value of current flowing through that particular element. So in this equation, this we indicate voltage across that particular element, and this I indicate the value of current flowing through that particular element. For example, if you have say 2 resistors and they are connected in series combinations like this. Suppose this is say R1 and this is say R2. Because they are connected in series, and we know that the fundamental property of series element, when 2 or more than 2 elements are connected in series, the value of current will remain same. So same value of current is flowing through R1 and the same value of current is again flowing through R2. Because the current is flowing from point A to point B, we know that current is always flows from higher potential to lower potential. That's why this point is going to be plus and this point is going to be minus. In the same way, with respect to resistor R2, current is flowing from left to right. That's why this point is going to be plus and this point is going to be minus. The moment we have a flow of current I through a resistor R1, this particular element will experience a voltage. Let us consider that the voltage V1 is I into R1. In the same way, the voltage across resistor R2 is V2, which is again going to be equal to the value of current flowing through resistor R2 multiplied by its effective resistance, which is nothing but R2. Now suppose if you want to calculate what will be the power across element R1, let us consider that the value of that power across element R1 is indicated by symbol P1. So I can write P1 as V into I. But in this case, V indicate the voltage across resistor R1. And from this figure, it is very clear that voltage across resistor R1 is nothing but V1. So I can write here as P1 is equals to V1 multiplied by current flowing through resistor R1. Now in this figure, the value of current flowing through resistor R1 is nothing but I. So it is simply V1 into I. Or I can also calculate the value of power by using this particular formula, which is nothing but I square into R. Now in this particular equation, what is I? I indicate the value of current flowing through the same particular element across which we are trying to calculate the value of power. So our objective is to calculate the value of power across resistor R1. So this P1 is going to be equal to I square into R. So here I is the value of current flowing through resistor R1. So here it is going to be equal to I square into R1. In the same way, I can also calculate the value of power P1 across resistor element R1 like V square by R. But remember one thing, this V is nothing but the voltage across that particular element. Now in this case, voltage across that particular element is say V1. So I need to write here as V1 square divided by R1. But we know that what is V1? V1 is simply I into R1. So I can write here as I into R1 whole square divided by R1. And if we solve this, we can write here as I square into R1 square divided by R1. Now this R1, this square will get cancelled and we can have the formula as I square into R1, which is exactly the same which we have written previously. See this one. So the basic objective is we have three formulas to calculate the value of power across any particular element. We may use V into I, we may use I square into R, we may use V square divided by R. But when to use which formula, that is very important. The thing is that if we are interested to use VI, this V and I must be a voltage and current flowing through that particular element. In the same way, if we are interested to use the formula I square into R, then in that case, this I has to be a current flowing through that particular resistor. In the same way, if you are interested to use the formula V square by R, then in that case, this V must be a voltage across that particular element. This is very, very important. And normally, this I square into R formula is used when the elements are connected in series combination. Why we need to use this particular formula? Because in series we know that the value of current is same. That's why we don't want to exert any additional formulas to calculate the value of V1. Because suppose if the elements are connected in series and if you are interested to use the formula V square by R, so first of all we have to calculate what will the value of voltage across each element. So this formula is applicable when the elements are connected in parallel combination. Because in case of parallel combination, the moment we connect the elements in parallel, the value of voltage will remain same. So we don't want to use additional methods to find the value of voltage. Straight away, because the elements are connected in parallel, so there will be a same value of voltage, so we can apply the formula directly, which is nothing but V square by R to calculate the value of what? Power. So this is very important. The thing is that you have three different formulas. You may use any one of the formula, you will get the same value. The thing is that you should apply the formula in correct sense. This is very important. Now let us try to discuss the sign convention for power. So sign conventions are very important. Like we have discussed the sign convention for current, the sign convention for voltages. In the same way, we have the sign conventions for power also. So what is the meaning of this? See here. Let us consider that we have a passive element indicated by symbol R, and this particular point is say plus, and this particular point is say minus, and there will be a flow of current from higher potential to lower potential. Now, with respect to passive element, why these elements are called as passive? Because they will always consume energy, they will not supply energy, and based on that particular terminology, we can define this particular element as passive because they are not going to supply energy, they are going to consume the energy. So, with respective the passive topology, or you can say voltage drop topology, or sometimes this particular topology is also known as load point of view technique or terminology. We can define this particular power as negative. Why? Because as far as power is concerned, power is simply a product of V into I. Now, because we know that it is a passive element, it will never supply energy, it will never supply power, it is always going to consume the power. That's why, with respect to load point of view, the power is always delivered as a negative sign. Suppose if you have a source like this point is say plus, this point is say minus, and we know that because it is a source, so we can treat this particular element as active, and it is always going to deliver a power or always going to deliver a energy, and the value of current delivered by this particular source is indicated by symbol say I. So current is always going to emit from the positive terminal of this particular element, and with respect to this particular point we can treat the power as positive. So whenever in the circuit we are having a active element which is capable to supply energy, which is capable to deliver energy, that we can treat as a positive power. Wherever we have a passive element which is not going to supply energy, whereas they are going to consume energy or they are going to store the energy, then with respect to that we are going to take power as negative. This is very important. You may change the terminology, you may take power supply as negative, then in that case you have the flexibility to take power absorbed as positive, or it may possible that you may take power deliver as negative, then in that case power absorb is going to be a positive. The thing is that it totally depends upon you what topology you have implemented. The thing is that when we are dealing with passive element, it is very clear that they are going to consume the power, and you can treat that particular term as negative. In the same way, if you are dealing with active, they are always going to supply the power, so this we can treat as positive, or you may interchange them. If you take power supply as negative, then in that case power consumed is going to be a positive, or they are vice versa. The thing is that once you have decided a topology, irrespective of the network, the topology will remain the same. For example, if you are solving a network and in that network you have a combination of active and passive element, and suppose you consider that power delivery is positive, then in the same network power absorbed, you are always going to be a positive one. or if you consider power absorbed as negative, then in that case power delivered is always going to be a positive one. So this you have to remember. Now, based on this, let us try to solve some numerical. So whatever the topic which we have covered till now, let us try to solve some simple numerical on this particular topic. And the first numerical is, let us consider that we have some 4600 electrons, and our objective is to calculate the net charge on these electrons. So how to calculate this? The first numerical is, our objective is to calculate how many number of charges are represented by 4600 electrons. So how to calculate this? It is very simple numerical. It is simply a formula based numerical. The thing is that you should know what is the charge available on each electron. So we know that charge available on each electron is minus 1.6 into 10 to the power minus 19 coulomb. So this minus 1.6 into 10 to the power minus 19 coulomb indicate the charge on one electron. Now our objective is to calculate how many number of charges are available or represented by these many number of electrons. So what we need to do? We need to simply multiply this 4600 by minus 1.6 into 10 to the power minus 19. So charges represented by 4600 electrons are simply 4600 multiplied by minus 1.6 into 10 to the power minus 19 coulomb. So if you solve this, you will get the answer as minus 7.369 into 10 to the power minus 16 coulomb. So it is simply based on the fact that you should know the charge on one electron. Very simple numerical. Now let us try to solve another numerical. Now in this numerical, our objective is to calculate the value of current. And in this particular numerical, the charge is expressed by some mathematical equation. So we have the equation of charge as Q equals to 5t into sine of 4 pi t, and this charge is in millicoulomb, and our objective is to find the value of current flowing through that particular circuit at time t equals to 0.5 second. So this is what our problem statement is. So we have a charge flowing through a circuit expressed by a mathematical equation Q equals to 5t into sine of 4 pi t, and the charge is specified in millicoulomb. That means we need to multiply this by 10 to the power minus 3, and our objective is to find the value of current flowing through the same circuit at time t equals to 0.5 second. So how to solve this numerical? Again, it is very simple. See, we know that I is nothing but rate of flow of charge, so I can write I as dq by dt. So I can rewrite this equation as d by dt of q. Now what is q? Q is 5 into t into sine of 4 pi t, and this is in milli. That's why it has to multiply by 10 to the power minus 3. Now to solve this, what we need to do? We need to apply the property of derivative. Derivative of first into second plus second derivative of first, that's why. So if you apply the property, I can write here as first into derivative of second. So derivative of sine 4 pi t. So I can write this as cos of 4 pi t into du by dt, which is going to be equal to 4 pi. Then plus first into derivative of second plus second. So second is sine of 4 pi t into derivative of first, which is nothing but 5. And again here we need to multiply this by 10 to the power minus 3 because we have a milli factor with us. So I equals to, I can write this as 5 into 4, which is nothing but 20 t pi into cos of 4 pi t, then plus here we have 5 into sine of 4 pi t, and then if you close this bracket we have a factor of 10 to the power minus 3, which is nothing but milli. Now, our objective is to calculate the value of current at time t equals to 0.5 seconds. So, what we need to do, we need to replace this t by 0.5. So, the moment you replace this t by 0.5, so 4 into 0.5 is nothing but 2. So, this particular term is going to be 2 pi. In the same way, this particular term is going to be 2 pi. And we know that sine of 2 pi is nothing but 0. So, this particular term is going to be what? 0. But here we have cos 2 pi. Cos 2 pi is nothing but 1. So this particular term is going to be what? 1. So we have here I equals to 20 into t, where t is 0.5 into pi. And then we have a factor of 10 to the power minus 3. If you solve this, 20 into 0.5, which is going to be equal to this term, you can replace by this will get cancelled. 5 into 2 is nothing but 10, so it is going to be equal to 10 pi into 10 to the power minus 3 ampere. Or simply, we know that pi is nothing but 3.14, so I can write here as 10 into pi, which is 3.142 into 10 to the power minus 3. So I can write this as 31.42 milliampere. So milli is 10 to the power minus 3. So this is what the value of current flowing through the circuit, which is 31.42 milliampere. So in this way, we are in a position to solve numerically on simple mathematical formulas based on charge, based on current, and you may solve for power as well as for the energy. This is very, very important. So let us stop today at this particular point. In the next lecture, we are going to discuss the classification of network element. For example, if you are interested to design a circuit or a network, then how to classify the elements available in network or in circuit, like active and then passive, then how to classify active and passive based on the ideal conditions or the practical conditions. So classification of network circuit element we are going to cover in the next lecture. Thank you.